Hello children, how are you all? Hope you all are fine and doing well. My name is Naresh, welcome to our channel Physics Plaza. Children, in today's session we are going to start current electricity. And we will be discussing some basic concepts. What is electric current, what is a potential and what is a potential difference and their units, and we will learn how electric current, a potential and a potential difference are measured actually. Dear children, before that once again let us see what is electricity. Dear children, it is one of the important branches of the physics which deals with the charges. But basically, electricity is of two types, current electricity and static electricity. But what is the difference between current electricity and static electricity, and what actually we are going to learn actually? Dear children, so current electricity, it is a branch of the electricity only, but which deals with the charges which are in motion. Current electricity will be dealing with the charges only, but which are in motion. But whereas static electricity, dear children, so static electricity will be dealing with the charges which are at rest. It is a basic difference between current electricity and static electricity. But what are we learning, dear children? So we are going to learn about only current electricity. Children, before getting to the topic, I have a small question for you all. That is very simple question and a very familiar and a well-known question to all. What is that here? What is current? Children, come on, try. What is current? Just think about it. You might have heard so many times. What do you think about current? What is current? How can we define? Children, if my guess is right, when I ask you the question called what is current, immediately in your mind I think something is going like the flow of charges is called current. The flow of electrons is called current. The movement of electrons is called current, and some other things are coming to your mind like a resistor, potential difference or some other thing. But actually I can say that the current word, the current actually, what you are thinking and what I asked is completely wrong. What we are understanding also wrong actually. In fact, I can say that current is not only like related to the electricity, I can say that. It's not that, we cannot say that. Current means what, dear children? Current means something which is in flow. It's not like what you are thinking, flow of charges is called current. It is a wrong concept, it is actually. Don't get confused. Let me give an example. Sometimes what happens, we'll be watching a cricket or else some cricket match is going, but we'll be somewhere else. And we call our friend and we'll ask, what is the current score? Hey mama, what is the current score? Children, their current score means what? Not electricity score. The present score is very important. Or else sometimes when we reading the newspaper, something like we'll be reading about one incident and we'll be talking to our friends. And yesterday something went wrong. Now what is the current situation? Children, current situation means not electricity situation, present situation. Try to understand. Current situation means what actually is a present situation. So everywhere, even we'll be reading the current affairs, when the present, the things which are going actually be reading. So current means what? Something which is in flow, something which is happening. It's very important. For suppose, if water is flowing, then we can say that it's a water current. If when two bodies with a different temperature brought in contact, what happens? Heat will flow. Then that we can call it as a heat current. It's very important. It's very important. If air is flowing, then that we can call it as the air current. If water is flowing, that we can call it the water current. If heat is flowing, that we can call it heat current. Then dear children, if charges are flowing, then that we can call it electric current, but not current. It's very important, where we will have a confusion. It is a electric current. It's a very important. Electric current we should say actually. It's not current. Electric current. So electric current. Now I should ask it. So whatever the things which are going in your mind are related to the electric current, but not related to the current actually. So the charges, if charges are going from one object to another object, one charge body to another charge body, then we can say that yes, electric current is flowing. It's very important. But don't get confused. Actual meaning of current is what? Something which is in flow. If that something is of charges, then that flow only we can call it as a electric current. It's very important. Then mathematically, how can we define what is the electric current, what is its mathematical formula, what are its units, and how it can be measured? Let us see. Dear children, if here is a conductor, let us take, so that through this, if one charge q is flowing in a time t, then mathematically we can say I is equal to q by t. I is equal to q by t. Dear children, here what is charge here? Only single charge is flowing, let us say. A single charge is flowing in a very less interval of time. Then the current also will be very small. Very small. Means chota q, chota t. Then obviously the electric current also very small. It's chota, very small. So I is equal to q by t. Means charge per time will give you actually electric current. Which means what? The charges which are in motion constitute electric current. The charges which are in motion constitute electric current. But dear children, here only we will get one doubt actually. We all know very well that in a conductor, if you can take any conductor, dear children, so there are plenty of electrons will be moving. For suppose, let us take here is a conductor. So in this conductor, plenty of electrons are moving actually. Plenty of electrons are moving. But means as all electrons are in motion, and we are saying that the motion of charges constitute electric current. Then as motion of charges constitute electric current and all charges within the conductor are in motion, then the moment when we touch this metal or metallic wire, we should get shock, electric shock. But are we getting electric shock? No. Then what? Is the concept wrong? No. Concept is right only. The flow of charges gives you electric current. Then why are we not getting, though there is a flow of charges are there within the conductor actually? Dear children, here only we need to talk about net charge. It's very important. Net charge we will talk. So the best example I'll give you. For example, dear children, so in a ground, just let us take a school where playground is there in the absence of PT teacher. Then how the children will be moving? They'll be moving randomly here and there. So same thing happens at room temperature. If you can take any conductor if you can take, all charges, so they'll be moving randomly. Means there is no order or there is no discipline. All charges are moving randomly. So if you can take any area of cross section at any time, then the amount of charge which is flowing from left to right is equal to the amount of charge which is flowing right to left through this area of cross section. So the net charge will be at any time, dear children, the net charge will be 0. So we need to talk about the net charge. Dear children, the motion of charges is not actually electric current. It is not that. That charges, they should move in a particular direction. So particular direction of flow of charges will give you electric current. So why are we not getting electric shock when we touch like any metal, though plenty of free electrons are moving randomly here and there? The reason is that the net charge is 0. But whereas when you take a charged body, for example, it is connected with a battery, then what will happen? Just imagine a situation in that PT, like in the drill period only, when your PT master will be there, then PT master will make you all to move in a particular direction. In the similar way, here when it is connected to the battery, so battery will make the charges to move in a particular direction. And the charges, if they are going in a particular direction only, we will have electric current. It's very important. Okay, fine. So if Q is a charge which is flowing through the conductor in a time t, then mathematically we can say I is equal to Q by t. But dear children, here do you think that only one charge will go? It's not that. Plenty of charges will be there. Let us say n number of charges will be there. So then what we have to do? We have to calculate the total charge. See here, only for one charge we calculate current. But I want to calculate the total amount of current which is passing through the conductor. Then we have to calculate the total charge. Then how to calculate the total charge? It's very important. So total charge, first we need to calculate the total charge. So total charge is equal to the number of charges which are going. Example, let us say electrons. The number of electrons which are going into charge of each electron. Dear children, sometimes will represent a charge with a Q or E also. Don't get confused. Anything is okay. Okay, so the total charge, how can we calculate? The number of charges or the number of electrons into the charge of each electron. So this will give you Q is equal to NE, total charge it is. Total charge. So with this we can calculate total current. Then how can we calculate total current? Total current I is equal to the total charge flowing in a given time. Children, it's very important. Very means very much important. So I is equal to Q by T. So the rate of flow of charge, is called actually electric current. And children, here we also can express this electric current in terms of NET. I is equal to N into E by T. I is equal to N into E by T. So dear children, this formula we will use to calculate the electric current whenever the number of electrons and the given time is given, we use this formula. But whereas here I is equal to Q by T or I is equal to Q by T here, when total charge is given, when time taken is given, you can calculate electric current I is equal to Q by T. Then what are the units? Of electric current? Children, we know that the charge is measured in coulomb. The charge, electric charge is measured in coulomb, C-O-U-L-O-M-B. Dear children, whenever you are writing complete name of the unit, first letter must be small. It is not a capital letter, but symbol can be capital letter. Okay, whereas time is measured in seconds. Children, we know that I is equal to, finally we got it as a Q by T, or even we can write it is N E by T also. So depends on the data given, we can use either this formula or this formula. Now let us see the units. So what are the units of electric current? Children, as we discussed, charge is measured in coulomb and time is measured in second. So electric current is measured in coulomb per second. But dear children, this coulomb per second only we can call it as a ampere. It's very important. This coulomb per second only we can call it as a ampere. Children, again I am saying you here, whenever we are writing the complete name of the unit, first letter should be a small. Sir, what happens when we write a capital A? When you write a capital A, it becomes scientist name. Try to understand. So here we have to write. If not, in a shortcut you can write as a capital A. But children, what is ampere? Here? Let us see here. For example, here is a conductor through which 1 coulomb charge is flowing in a 1 second. That is, if Q is equal to 1 coulomb and time is equal to 1 second, then current will be 1 ampere. Means if 1 coulomb charge is flowing in the conductor in 1 second, then the current is equivalent to 1 ampere. Then dear children, how can we measure the electric current? Dear children, we measure the electric current by using a device called ammeter. It's very important, dear children. So here, ammeter is a device which is used to measure the electric current in the circuit. And ammeter is always connected in series only. Dear children, why ammeter is always connected in series? Then that will be discussing in the series and the parallel combination of resistor. There will be discussing why always ammeter must be connected in series only. Okay, dear children. So this is what actually electric current. I repeat once. What is electric current? The rate of flow of charge is called electric current. Mathematically, we can define I is equal to Q by T. But here, how to calculate the total amount of charge? The number of charges, the number of electrons into charge of each electron by time actually. Then what are the SI units of electric current, dear children? It's the amperes, that is coulomb per second. How can we measure the electric current? By using a device called ammeter. But dear children, then how does, so as we are saying that it is a flow of charges, means current can flow. Still, it's very important. It has some particular direction. For example, let us take here only, it is a point A, it is a point B. So point A to point B current is flowing. How much amount of current is flowing? In this case, 1 ampere current is flowing. So that 1 ampere is a magnitude. And what is its direction? A to B. Then what can you say about electric current? Is it a scalar or vector? Generally, what do we think? Yes, it has a magnitude and it has a direction. Then we think that it is a vector quantity. Because we might have studied somewhere else. The physical quantity which has direction and a magnitude is called vector quantity. But dear children, here electric current, surprisingly, it is a scalar quantity. It is not a vector quantity. Why? Means the definition whatever we are thinking is not completed, it is incomplete definition. Then what is a complete definition? So a physical quantity should have magnitude, direction, and as well as, my children, it must obey the law of vector additions. Very, very important. So here electric current can have magnitude, it has direction, but it doesn't obey the law of vector addition. So electric current is a scalar quantity. It's very, very important. Electric current is a scalar quantity. Important. How does the electric current flow? It's very, very, very important, children. So before going to that, children, just let us take a few examples to talk about the direction. Then we can come to the what a conclusion regarding the direction of electric current. So just imagine a situation where a ball is placed B. Okay. Then what will happen here? Will it come downward direction in general in a normal condition? Will it come downward direction or will it go upward direction? So obviously we can say that the ball will fall. The ball will come towards the earth only. Means here the ball or object is moving higher gravitational potential to lower gravitational potential. Very, very important. Higher gravitational potential to lower gravitational potential it is moving. Very important. Whereas, dear children, look at here. So in this case, two bodies with a different temperatures are brought in contact. Dear children, whenever two bodies with a different temperatures are brought in contact, so there will be a flow of heat. But you tell whether the flow will, like a heat flow will be A to B or B to A. It always from, dear children, body of higher temperature to body of lower temperature. Body of higher temperature to body of lower temperature. Whereas, look at here. So two vessels with a liquid but in different levels are connected with by means of a horizontal pipe. Then what will happen? The water flow will be from A to B or B to A. Obviously, we all can say that it is A to B only. Why? Water always flows from higher hydrostatic pressure to lower, that is higher level to lower level. Higher level to lower level. Then what about air, dear children? Let us take the case of air also. Higher pressure to lower pressure. So observe in all these cases, dear children. So higher gravitational potential to lower gravitational potential energy. Here higher temperature to lower temperature. Here higher level to lower level. Whereas in the case of gas also, higher pressure to lower pressure. Means what? Conventionally everything is going from higher to lower only. So that is the reason why we also will discuss that electric current always flows from what? Higher potential to lower potential. Means there should be some difference. There should be some difference to flow something. According to this is what actually we understood. So electric current always flows from higher potential to lower potential. This is very, very important. But the dear children, here one surprising thing is there. Current is flowing from higher potential to lower potential. But the electrons will move from lower potential to higher potential. Of course, there will be a confusion. What is this? The current is flowing in one direction, but electrons are going in another direction. Of course, opposite direction. Then how to understand? Just we'll see with a small figure, dear children, we can get a complete picture. What is the direction of current? What is the direction of electrons? Let us see once. So look at here. Here two charged bodies are there. Let us say it is a body A, positively charged one, and here is body B, negatively charged one. If these two charged bodies are connected with one conductor, let us say, connect the conductor. This is very, very important. And positively charged body is said to be at a higher potential. It's very important, children. Said to be at a high potential, whereas negatively charged body is said to be at lower potential. That is low potential. Low potential. So what happens when these two charged bodies are connected with a conductor? Children, this is what very important to understand the direction of current and the direction of what? Flow of electrons. Is very, very important. Dear children, here as it is a positive charged body, so your majority carriers are all positive charges only. Whereas as it is a negatively charged body, negative charge is completely in this majority carriers are what? All negatively charges only. One more thing, it is a completely assumption only, because in a conductor, in any given conductor, do you think that positive charges will move? No, it is a electrons will move. But in order to understand the concept, we are assuming. So what happens now when these two are connected? Now dear children, one more assumption let us take. One more assumption. It is completely assumption only. Let us take here and there one like this 4 negative charges there. Children, it is not possible like negative charges cannot stay with the positive charge. Again you may get this, they'll get neutral. Just this assumption, just assumption only. So whereas here also, let us take 1 or 2 something like this positive charges. Now what happens when these two are connected with the conductor, dear children? And we know that definitely the diffusion takes place. Means here, dear children, here more number of positive charges are there, will move to the point where less number of positive charges. Whereas here more number of negative charge, negative charges are there, definitely they will move towards the point where less number of negatively charged particles are. It's a common thing. It's a very common thing. So I can say that here through this like this, dear children, what will happen? Positive charges will move. Positive charges will move from A to B. Positive charges will move from A to B. But for this reverse direction, what happens? So as here more number of negatively charged particles are there. Here less number of negatively charged particles are there. So what happens here? This negatively charged particles, negative charges will move from B to A. So in this direction they will move. Dear children, in this direction they will move. In this direction, here negatively charged particle is moving. Negatively charges are moving. Try to understand, dear children. So positive charges are moving from A to B. That is higher potential to lower potential. Whereas negative charges are moving from lower potential to higher potential. Children, it's very important. So the flow of positive charges, the flow of actually positive charges only constitute actually conventional current. Dear children, the direction of flow of positive charges, we can take it as a conventional current. Dear children, there are 2 types of currents we will discuss. One is conventional current. The conventional current is due to the flow of positive charges. Then what about here flow of negative charges? The flow of negative charges, we can take it as a electronic current. So conventional current always flows from higher potential to lower potential. Whereas electronic current, that is the motion of the charges, the motion of the electrons, always from lower potential to higher potential. So dear children, so this is a conventional direction of current only. We will consider as a direction of current. I repeat once again, the direction of conventional current only, the direction of conventional current, that is the direction of motion of positive charges only, we can take as a direction of electric current. Then what about the direction of electrons, dear children? So the direction of electrons is always opposite to the direction of current. Current means what here? Conventional current, dear children, conventional current. So here electronic current is always opposite to the direction of conventional current. Direction of conventional. Hope it's very clear. So dear children, so here current always flows from higher potential to lower potential. But what about electrons? The electrons will move from lower potential to higher potential. That is opposite to the direction of current. But dear children, here one word you use actually, potential. Yes, now we just we are concluding that okay, current always flows from higher potential to lower potential. Then what is this potential? Children, it's very important. Now let us discuss what is the potential, what are its units. Whether more amount of current should flow or less amount of current should flow. So this is what actually the potential difference only will decide. But what actually potential difference, dear children? So before going to that, just you forget about the potential difference. Let us come to the our common daily life, where here one object is there. For example, this object is there at a point A. Object is at a point A. Now I want to bring this object A to X place, somewhere else, some. So this object must be brought or must be taken from point A to this place. So do you think that will it go when we call someone, hey, object can come means? No, it's not that. It won't go, man. What happens? Some force must be acted on it. So that body must be displaced. Body must be displaced. Then only what will happen? A body is sent from point A to point X. Means oral, or just you think orally what is happening here? Some work is done on the object. Work is done on the object here. Very important. So some work must be done here to move this object from point A to a point X. It's very important. Then you may get found out, sir, what is this? Work means that we learned in a work per energy. Then how can we relate to this electric current? Children, that's what we are coming to that point. It's very important. So now in the place of this, what we can say an object, children, you can imagine a positive unit charge. You can imagine positive unit charge. This is also called as test charge. This is also called test charge. Children, what is a test charge? Actually, there is no test charge. It is an ideal concept. Completely, it is an ideal concept. But still, though it is ideal concept, what is actually test charge? Dear children, the charge which does not influence other charges, but whereas the charge which is influenced by other charges. I repeat once, don't get confused. The charge, for example here, let us take here one charge is there. Okay, and here one more charge is there. So obviously, dear children, if two charges brought here, might be both like or unlike, whatever it may be, definitely each charge will exert some force of attraction or force of repulsion on each other. It's common. It's common. But in this case, let us say here, this black color one, whatever I am showing, let us say this charge only. Okay, now. So it exerts some force on this. It exerts some force on this. Means here what is happening here? This red color charge is influenced, is exerted by some charge. What are some force actually? But in reverse, this red color charge do not exert force, as do not show any effect actually. Then such type of charge we can call test charge. It is highly impossible. It is not possible. It is not at all possible. So the charge which is influenced, but which does not influence other charges is called actually test charge. So like that is completely its assumption concept. It is not true actually. So let us assume that here there is a positive unit charge actually. We have taken positive unit charge. Now I want to take this positive unit charge from this point to here somewhere else. Let us say here is some electric field. Here some electric field is there, children. So I want to send this unit positive charge from this point to a point in electric field. For that, definitely there must be some work done. So definitely there should be some work done. It's very, very important. But the thing is that where this point is there, let us assume that this point is at infinity distance. Let us say, wherever it may be, it is at a 10 meters distance, it is at 100 meters distance, it is at 1000 kilometers, it is at infinity distance, whatever it may be actually, whatever it may be. So we have to do means some work must be done in order to move a unit positive charge from one point to another point actually. But here, what is the distance? We cannot define the distance. We are assuming that this unit positive charge is there at infinity. So in order to bring this unit positive charge from infinity to a point in a electric field is called actually, the children, is called. So for that some work should be done. That work done only we can call it as a electric potential. So to move this charge, let us suppose capital W is a work done to move a charge of Q. Then mathematically we can define potential at a point is equal to W by Q it is. Children, it is mathematically electric potential is equal to work done by Q. Children, what is the definition of electric potential? So the amount of work done to move unit positive charge from where? Infinity to where? To point in a electric field is called electric potential. So the amount of work done to move unit positive charge from infinity to a point in a electric field is called, children, electric potential. So mathematically it is V is equal to W by Q. Then what are its units? Teachers? Very, very important. Children, W is measured in joules. Whereas Q is measured in coulombs. So then potential is measured in terms of joule per coulomb. So dear children, this joule per coulomb only we can call it as a volt. Again repeat, dear children, the first letter should be small. If you can take a capital letter, it will become a scientist name volt, but not a unit. Okay, volt, and it can be capital, symbol can be capital V. Then how can we measure, dear children? So electric potential is measured by a device called voltmeter, not voltammeter, dear children. Whenever you are writing a spelling, there also you must be very careful. Voltammeter is different. It's very different. So here we are using voltmeter. Voltmeter is used to measure the electric potential, and it is always connected in parallel. Now, dear children, we will discuss what is a potential difference. Very, very important, because there should be some, as I said, that there should be some potential difference. Then only there is a flow of current. So now we will discuss potential difference. Yeah. Children, let us assume here is a conductor, and it just assume that it is in like within the circuit. So at a point A, some charge Q is there. Now this charge must be moved from point A to point B. But as we discussed, anything is moved when some work is done. Anything is moved from one point to another point, but some work must be done. So dear children, in this case also, let us say here at a point A, the potential is VA, whereas at a point B, let us say potential is VB. Already B is there, so it is a VB. Now we want to move a charge from one point A where the potential is VA to point B where the potential is VB. For that, some work must be done. So this work done only we can call it as a potential difference. Children, getting confused? There is a very slight difference is there. In order to define the potential, we consider the unit positive charge at infinity. Means the distance is not defined, it is undefined. But whereas teacher here, the distance between these 2 points is a defined. It's very important. So here, how to define electric potential difference? The amount of work done to move a charge from one point to another point within the circuit. It's very important. So children, as you know, the charge is always moved from higher potential to lower potential. Then potential difference VA minus VB is equal to, as usual, it is a work done by charge. So the amount of work done to move a charge from one point to another point is called potential difference between that 2 points. Children, what happens if this point B is at infinity distance? Children, at infinity, potential is 0. Then this will become 0. Then again, we will get the concept of what? Electric potential only. Children, try to understand. If this point is chosen at infinity, potential is 0. So this VB will be 0. Again, you will get V is equal to W by Q only. Then what are the units? As usual, dear children, here as work is measured in a joule, charge is measured in coulomb. So here potential difference also has same units like a joule per coulomb, and this also we can call it as a volt, that is a capital V. And potential difference also is measured by using a device called voltmeter, and it is always connected in parallel only. But dear children, so one more very important thing. When we can say that the potential difference between these 2 points is 1 volt, it's very important. Even in exam also it will be given like this. The potential difference between 2 points is a 1 volt. Explain the meaning. What is the meaning of the given statement? Let us see, dear children. For suppose here 1 coulomb charge is there. So in order to move this 1 coulomb charge from one point to another point, if 1 joule work is done, then we can say that the potential difference between the 2 points is 1 volt. That is, if W is equal to 1 joule and Q is equal to 1 coulomb, then what happens, dear children, here? VA minus VB is equal to 1 volt. That is, if 1 joule work is done to move 1 coulomb charge from one point to another point, then the potential difference between that 2 points is equal to 1 volt. It's very important. Okay, children. So these are the 2 basic, very important concepts. What is electric current and what are its units, and especially, children, the direction of electric current is very important. And whereas what is the potential and what is a potential difference. Dear children, in next session we will be learning about one more very important concept called resistance. What is the resistance and what are the factors on which it depends? There we will be discussing even Ohm's law also. Thank you so much. All the very best.